Yeah, that's it's just a little okay at the top of the. Oh, yep. Okay. Sweet. Maybe I'll stand here for other people on Zoom. Okay, let's get started. So, first of all, thank you guys for coming. There's a lot of new faces today, which is great to see. I'm Liam. This is the McGill Music Research Club. Basically, we have meetings once a month where somebody presents. We have a discussion about research in music, different area every month. Last month, we had a theory PhD student, Aidan McGartland, present about integral serialism. This time we have music and AI, which is an exciting topic. So thank you to all the people here from Kermit and abroad and elsewhere for coming. Please help yourself to food and snacks. It's for you guys, paid for by Kermit and the MGSS. And before we get started, just a reminder to follow us on Instagram at McGill Music Research. It's the best way to keep up to date with our meetings if you're interested, or you can also talk to me and I'll add you to the mailing list if that's more convenient for you. So without further ado, it is my pleasure to introduce Ziyu Wang from NYU and Abu Dhabi, which I just learned global international presence. He's going to be talking about music and AI. Thank you.
Okay, thank you, Liam, for the introduction. And I'm happy to come to McGill and to give a talk on music AI. And yeah, so today I'm going to talk about concepts and control. It's understanding creativity with music AI. Let's begin with a bit about myself and what I mean by the in the title, what I mean by say concepts and control, and we are exploring the creativity with music AI. So I'm a musician and also a computer scientist. As a musician, so I play the piano and erhu from the age of 3, and later I try some conducting, and I also direct musical theaters in my undergraduate, and now I'm trying to do some composition. Yeah, of course, I know this is a music school. I'm not in all these areas. I'm not a professional musician, but I'm say I experienced all these forms of arts, and I learned that music is really a very smart way to express ourselves, to turn lifeless things into something that can convey emotions. So I'm really interested in this kind of creativity. I ask, how do human minds appreciate and create music? And I try to solve this problem from a computer scientist perspective. I believe the best way to understand music intelligence is just to recreate it. Just like when Alan Turing first built a computer, Alan Turing believed that only by recreating something that we can know that how people think. And that's why I build deep generative models to compose music, and we have the research domain of automatic music generation. In music school, I really feel it's a little bit worried to discuss this topic for you guys, because actually for musicians, we really don't need that much of AI to help. And as far as this is my opinion, that if I do this research, it's actually for an experiment. Just replicate, try to replicate our human creativity. And still, we cannot fully replicate this and try to see how much, like, say, artificial intelligence can go in the domain of music composition. And I'm going to give you a history of how this topic explored over time. Let's roll back to 2008. And at that time, we have a very famous model called MySong. The goal for this model is just for a music novice, they sing some melody and they try to capture the melody and try to harmonize and give you a piano accompaniment with some simple texture. Let's look at this video to see how it goes.
Creating music with MySong begins with recording a vocal melody. A user presses the record button and sings along with a computer-generated beat.
I'm all below, and the world is cold. I will feel a glow just thinking of you and the way you look tonight.
When the user stops singing, my song immediately generates a set of chords to accompany the user's voice. The user can listen to these chords as a piano accompaniment.
Someday, when I'm all below and the world is cold, I will feel a glow just thinking of you and the way you look tonight.
Because there are many accompaniments that are appropriate for a given melody, my song allows the user to adjust the chords chosen by the system using parameters that are intuitive to non-musicians. One slider bar allows the user to make the accompaniment happier.
Someday, when I'm all below and the world is cold, I will feel a glow.
Or sadder.
Someday, when I'm all below and the world is cold, I will feel a glow.
Yeah, you get a sense. And the model at that time is actually the backend model is called hidden Markov model. And the idea is very simple. It's just to compute what kind of chord transitions, pairwise chord transitions is more frequent in the data set, and also to see whether this chord is good with the melody above. Just to compute how many pitches are they sharing, just like that. So for this model, we really understand how this model works. And if we see when we slide the happy factor to sadness, the chord doesn't work quite right. But we understand like this is the model behavior. So this is white box models. But of course, as you can see, the quality is not there. It is just like we know something and we replicate something just to replicate only partial of our understanding of music. And we definitely want more. So now it's 2018, and we have deep music generation, means we generate music by deep learning. What deep learning do is just to have a large data set of music, and the model will learn to predict what is the most possible next note. And this is a very famous work called Music Transformer. And let's see what's the generation result. So for me, it's kind of give us a sense of Schubert, and the quality is much higher. But we also find the problem that the music only can generate this kind of music style, and we really don't know. Say when we generate this piece, what can we use? Use the model for our applications, and how do we communicate with it? And now it's the time of large language models, and in our music domain, we actually have large audio language models, which is called Music Gen, just invented in 2023. And I just want to give you the sense that in current model, the audio quality is kind of powerful. But actually, when we really want to control and play with it, it is really quite limited. And I'm going to show you a task is ask this audio generation model to compose a Chinese style Mozart sonata. And because you guys are all good in music, I'm gonna play the Chinese style composed by human, okay, me in 2018. And let's guess which sonata is it. Got it? Okay. Okay. And yeah, if it is the original version is this. Yeah, and this is what I asked Music Gen to do. Just transfer this piano sonata to Chinese style, keep it as a piano sonata. I mean, the instrument should be piano and adopt Chinese elements in composition. I think for human beings, what we think about is maybe using pentatonic scale and maybe try some Chinese rhythm. And I've tried many times using Music Gen, and this is the result. So you see, it has a sonority of maybe Chinese national orchestra, but it's definitely not piano, and it's not using the composition technique. So you find that in actually music AI task, when the model grows larger, and you definitely hear the result by Suno, in all these kind of model, when you're really trying to infuse some composition idea into it, it really cannot help you. And this is the problem of the so-called black box model of deep learning models. And so the question is how to combine those white box, which are actually, we understand how it goes, but the quality is not good, and black box approaches, which they are quite strong in the quality, but they really understand nothing about the human control. And there are many ways. And in the mainstream approach, the way is just to create more data. So we have thousands of Chinese style Mozart and ask the model to train. And at the end of the day, it might have a chance to learn it. But now I'm going to talk to you about my research is what I believe is we're not going to teach it, say, what we want. Say we are feeding the data to the model, ask them, this is what we want. Instead, we are trying to give the deep learning model the perspective about how we think about music. And this is really important. And the most creative part is how to infuse these kind of how we think into the model. I'm always using a metaphor of this situation. Say, if we want to work with someone else, and well, if we don't know how they think, and we are just giving them instructions, just like giving them data, ask them to do this and do that, it's not gonna work. But if once we understand their intuition and their motivation, we know what kind of word we can tell them, and you're more in sync, and the cooperation is more natural. So I believe it is same with working with music AI. And this is the big picture of my research. And most of my research is diving into this first topic, is could human knowledge help us build better AI systems? We are trying to infuse the music knowledge we know in a model and see if it can be grasped a more reliable grasp of the music concept we know about. So I'm going to talk about first is infusing the music concepts. In our music composition, there are a lot of common concepts. For example, in melody, we have pitch contour, and in polyphonic music, we have accompaniment texture. Like these things are really hard to define by language. Like we say a melody is going up and going down, but it is not detailed enough. What we perceive is more than that. And the first goal is to try to learn a concept corresponding to this very nuanced thing and see if the model can grasp it. And to do this, we are going to use a very important technique in AI. It's called representation disentanglement. So the idea is like this. Let's say we have a data set of 4 cartoon figures: Garfield, Sonic, Sailor Moon, and Pikachu. And yeah, this is the data set. And we have to infuse our concepts about cartoon figures. Say an avatar is composed by 2 things, the face and the head. The face and head here are the concepts, and we want the model to learn it. And once the model can learn it, we can test whether the model grasps this concept by doing this generation task. Say we can recombine different faces and head, and we'll have 16 different cartoon figures. And this idea is also worked in the music domain. So if we are working on music and think about melody, what are the attributes we want to disentangle? So it's pretty obvious, like we're trying to disentangle the pitch contour thing and also the rhythm. It is the first impression, and we're trying to work on that. And the model we're using is actually called a variational autoencoder. So the idea is here, the X is the music we want to learn, and here is the model architecture. The model encodes this X into the latent space, and finally decode the output. The training objective is just to reconstruct the output to be same as the input. And because there is a latent space and we add some Gaussian regularization here, we ensure this latent space is quite compact. Yeah. So, and what we're interested in is just this latent space. We think about this latent space as maybe like a knob. We want to say a latent or a compression of the original input means we're learning a knob that can control the generation of this output. And by disentanglement, we are just say we cut this knob into two halves. We want to separate two knobs, and we want to control them separately. And the idea to separate rhythm and pitch is because we already know what is pitch, right? We already know what is rhythm. The rhythm is just a sequence of onsets, sustain, and rest. And we ask the model to have a grasp of the rhythm side, and we just leave the left-hand side to be whatever is left behind. And the model will learn what is left behind must be something related to pitch. So in this sense, we achieve this representation disentanglement. And I'm going to play you the demo of how we disentangle melody and disentangle pitch and rhythm. The original melody sounds like this. And you can think about the pitch contour aspect and also the rhythm aspect, right? It's like a folk song. And in the first experiment, we change the rhythm of this piece, but maintain the pitch control. The rhythm we are showing is very extreme. It's all 16th note, like that. Yeah, and the result is, yeah, so this is like a very good realization of all 16th note instead of da 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 da. Okay, and then we try to use another pitch contour. This is going up and going down, and it should be realized in this rhythm. So the result is going up and down. And also this model can be controlled by different chord. So if we change a different chord, it will get. So in this case, this is what I mean by disentangle the pitch and rhythm factor. Let's move on to polyphonic music. And if we are thinking about piano accompaniment of pop music, the most intuitive idea is to disentangle chord and texture. For chord side, we have different chord progressions, and on the texture side, we know we can use arpeggio, abated bass, broad chords, etc., to accompany the music. And we can think about these two. We can use the same accompaniment texture and play different chord progressions. So this is a valid disentanglement problem. And we are also using a VAE, the variation autoencoder-like structure to learn that. So on the left-hand side, we use the chord encoder here to encode the chord information into latent chord representation. And on the right-hand side, this is a special design of the neural network. We try to design a very pitch-insensitive encoder, because in the convolution network, we can design the stride size to be very, very large so that the model of right-hand side, it is very nearsighted. It cannot see the pitch clearly. And in that sense, we hope to encode the Z texture information to be pitch insensitive and only capture texture. And finally, we try to combine these two representations together to reconstruct the final music. And in this case, we successfully disentangle the texture side and the chord side. And here is the demo. So I guess you cannot see it clearly, but you probably can have good ears. So what I'm going to do is I try to combine the texture of the left-hand side and the chord of the right-hand side and get a final composition. So I'll play the first one and focus on the texture it is using. It is mainly arpeggio on left hand, and right hand is melody. And I cut out. Yeah, so for this music, I want to borrow everything about the texture. And on the right-hand side, I want to borrow the chord progression. Yeah, so the chord is totally different in different key, and this is the result. So, hand on top and right hand on. It's just like a musician when he learns how to play some arpeggio texture and he try to practice it on different chord progressions like that. So now we have this entangled monophonic case and polyphonic case. I'm thinking about what application can give. And what I think about is this audio to symbolic arrangement task. So the task is like this. This is the input. Yeah, so this is say an audio but containing multiple instruments, can be in drum and in guitar, etc. And musicians know how to arrange it into a piano composition like this. Here we take the drum. Yeah, so this is the task, and the mainstream approach to do this must be we first transcribe this input audio to some sheet music, and we'll try to do piano reduction. And this is the technical way to do this. And I'm thinking about when musicians do this, it will have a concept or representation about the input audio, how it sounds like, and directly use this idea to arrange to piano composition. And I try to leverage this kind of representation learning idea to this task. So the idea is still the disentangled chord and texture, and we want both factors to be affected by an input source of audio in the composition process. And this is hard to train because, for an audio file, there could be many possible ways to arrange a symbolic piano music. So I try to use a transfer learning-like technique. So the model is like this. At the beginning phase, this is a symbolic model. So everything is trained similar to the previous study for chord and symbolic texture. And as the training progress, I'm going to gradually shift the focus from the symbolic side to the audio side, just like this. And finally, the model is solely depending on the chord and the texture information from the audio. And it makes this audio to symbolic work. I'm going to play you a demo of how the model generates. This is the input pop audio. Good job. Yeah, and in this system, what we do is we get a sound and we use source separation to separate into the vocal part and the accompaniment part. For accompaniment part, we use MR algorithm to get the chord and the beat information. And then we can quantize this audio or time stretch this audio into measures. And then I use my algorithms to arrange different measures of the audio into the piano accompaniment. And then I try to merge the piano accompaniment and the vocal together. And then I get the final output. And let's listen to it. This is the intro. It also learns how to build up. Vocal enters.
如果你就当你是错的人，有些错我们都要负责任。
Yeah, it's like that. And so this concludes the first part where I try to learn the music concept commonly used in pop music composition. And specifically, the control can be given from the symbolic side and also coming from the audio side. So in this demo, I try to interact with a robot and ask it to arrange the accompaniment of Fly Me to the Moon. And I'm asking him to do style transfer. I give him first an audio, and I want to say, can you arrange a piano cover based on this audio? And then I play something on the keyboard, say, can you arrange a ragtime-like thing to arrange this accompaniment? And the robot tries to do that. Let's enjoy the demo.
Hi, Teo.
Hi Ziyu, hope everything is well in Music X Lab. Recently, I learned how to do piano accompaniment arrangement for pop songs. Would you like to arrange a song that you like?
Sure. Now I'm playing Fly Me to the Moon, the famous song. I'm very interested in one version. Shall I play two? Here it goes. Can you try to arrange a piano cover for this?
That's a piece of cake. Let me process it.
Fly me to the moon, let me play among the stars. Let me see what spring is like up to blue and Mars. In other words, hold my hands. In other words, time is new. Wow, this is great. If this is easy for you, can you try harder, like use exact the same texture of this piece? This one is ragtime. Can you try to use this to arrange Fly Me to the Moon?
It's hard, but I believe I can also do it. Do you want to take care of the vocal part this time?
Sure. Fly me to the moon and let me play among the stars. Let me see what spring is like on Jupiter and Mars. In other words, hold my hand. In other words, I love you. Great, thank you, Teo.
You are welcome.
So hope you enjoy the demo. But I have to confess, so I'm the designer of the algorithm, and all the music demo you heard is actually pre-rendered, on our computer, and this is just a demo to showcase the generation results. So the generation result is actually fed to the robot, and the robot play, and it is give you the impression as if it is generating real time. But we hope it to do it in the future. And yeah, so this is the first part. And the next goal I want to reach is I have this kind of knob to disentangle a piece of music into two factors. And if we want to compose whole song, it's really difficult to define all the knobs and using disentanglement to disentangle everything. And the actual music composition process must be like this. There are a lot of knobs and we don't know what are the meanings. composers can even not verbalize their mental process. So this research path probably will be a dead end. And the next methodology is how to learn music structure. And we have to provide some ways for AI to learn what is hierarchical planning. And I'm going to begin with a very interesting work about how to let machine learn how to compose a whole song. For now, all the music AI can only compose a short segment of music, about 30 seconds. And it is just a segment. There's no beginning and not an end. There's no idea about what's the phrase structure and anything like that. So to enable a model to compose a long whole song, I have to teach model hierarchical planning. I'm borrowing an idea from something we already know. Say there are 3 levels of music notation or representation. Music score is the abstraction of everything. And if we elaborate it, we can add some expression into it, and it becomes some performance, something like a MIDI control. And based on the performance, if we add something called timbre, it will become more finer grained. It will become the audio we hear. And the question I want to ask is, are there upper levels? And if we have an abstraction of the music score, we can achieve long-term generation. So what I try to define 4 levels of language for whole song generation. And this is, I try to define this 4 level, only it works good for pop song and it is easy to extract. And I believe there are many possible ways to define the hierarchical language. And I would introduce it in the next slides. And also here I introduce like different stylistic control on each level. And these are, say, chord, rhythm, texture. And these are just, the representation or the concepts that I learned in the first research step. So in this case, I'm showing you a way to group all these knobs into a hierarchical entity so that the generation will be viewed as a whole. And this is the definition of the hierarchical music language I tried. There are 4 levels. The top level is form. It contains the key of the music and also the phrase structure, like the form, the intro, the verse, chorus, etc. The second level is reduced lead sheet, containing reduced melody and reduced chord. And next level is lead sheet. It is the original vocal melody with the chord. And the final level is the music score. It's the melody with the underlying piano accompaniment. And I'm trying to generate it from a hierarchical way. Say I generate the first top level, and then the rest of the level condition on the top level. And I will try to use the diffusion model, which is an image generation model, to generate it. So I try to convert every music language to image, like the piano roll we learn. And in this case, we can generate it with, say, image generation algorithm. The idea is like this. So this is the diffusion model. And the idea is I want to generate the image of a piano roll. As here, the X naught shows the piano roll. And the image generation model is, say, I can generate it from the white noise. So at the beginning, everything is noise, and gradually it will be clearer and clearer, and finally get this piano roll. And this mimics the idea is at the first point, our composition idea is just white noise. There are many possibilities. And as our thoughts progress, our idea about what the music actually is will be clearer and clearer. And this is implemented into 4 levels of the diffusion model. So there are 4 levels of model. Each level, I train a separate diffusion models. And the generation process is like this. At first, say all 4 levels are white noise because we have no idea about it. The model first use the first level model to generate the first level of language. So now this is known. And for form language, it is really very coarse so that the model can actually generate at, let's say, 256 measures. And it will be a very long music in theory. And after generating the form, it will generate the second level. And because the resolution will be finer, so the scope will also be finer here. So it will use the second level language the model to generate the second level, only the first part. And then it will shift the focus to the next window with a hop size. And then it will generate this noise part with diffusion model. And we get this. And in this case, so on and so forth, we get a second level language. And similarly, we use the third level model to get the third level language. And finally, the fourth level. And the whole sound generation is completed. I'll play you a demo of how the model performs. So in this case, I'm going to show you only 40 measure generation. In this generation, the music contains intro and verse and chorus and also bridge. And the verse and chorus appears many times. And what you're going to hear is for each time the verse appears, the model learns to use similar kind of music ideas, and it will develop the previous idea. And similar for bridge, the two bridges are similar, and the second one is more elaborate of the first one. And I'll guide you through the listening process. The intro. There's a cadence here. Verse. Verse again. Chorus. Bridge. Verse again. Chorus. The outro. So, when we finish this study, the model can generate whole song. It's very long, and it is only trained on, say, less than 1K pieces of music. And compared to what is the current large language model training, it is a really very small data set. And with this kind of hierarchical planning design, the model learns, say, the repetition of the similar music idea. It learns what is cadence, and also like what is the role of the bridge and intro and chorus, etc. And of course, the quality is still quite limited. The music so far is still like this. And this makes us to think the next step, which is if we have the structure, and can we use large language modeling to give us more quality? So similarly, in the next study, I'm trying to use this kind of hierarchical idea to the next step. Is if we have a symbolic music score, can we have the audio so that the audio generation can be more controlled? So in this case, I'm going to show you our work on fine-tuning a music gen. Music gen is large audio language model, and the original design is only taken a text control. So I can specify genre, timbre, emotion, etc. And in our work, I try to give the music content control, say our ideas about chords, drum, and also the piano roll information. And we want the model to help us elaborate this idea into the actual song we hear. And the idea is we fine-tune this music gen, which is a very large model, and we add these kind of control, chords, drum, and piano roll into the model. And we only feed it through the condition adapter. This is a very parameter efficient design, similar to the LoRa or Llama adapter, if you heard of that already. Basically, it is just we can tune only a little portion of the large parameters to make it work. And still, our method is very parameter efficient. We are only to tune only 3% of the original parameters, and we can train it with not state-of-the-art GPUs with only 300 sounds and in 5 hours, and it finished the training. I'm going to show you how the model sounds. So here I give the text control, say lazy jazz, with some instruments of saxophone, piano, and drums. And this is the music content control I'm giving the model. You will hear a piano roll played with a drum track. So this is kind of DAO and also similar to what I've already generated, just piano. And this is the final result. So we see that the music is richer, and we do hope, say, with this kind of hierarchical design, through fine-tuning, we can have a more controlled way of large audio language models. And I'm going to tell you another interesting study is just thinking about music hierarchy, not from the times axis. So we have verse, chorus like that, but we think about the composition process of composers. And this is a very interesting project. I'm working with another student I'm now advising. And he is very interested in electronic music. And I say, what about thinking what's the composition process? And maybe we can automate this process. So the current setting is simple. We have a library of music clips containing audio clips and MIDI clips. And we want GPT, just the text language model, to do the composition. And we are using the in-context learning technique. We feed GPT our data structure and several questions and answers. So what are the sections to compose? GPT will tell you intro, verse, chorus, etc. And what kind of audio and MIDI clips do you want? The GPT will provide some keywords of the clip we are going to use, and we are going to search in the library. And GPT will give, depending on the theme it composed, it will give you the corresponding keywords, which are quite useful. And then I will ask GPT like where to place these clips and how are they placed. So if they have to do a transposition or it should be repeated on beat 2 and 4, etc. And the generation will be very cool like this. Say on the DAW, it just copy paste everything on it. And if it's generating very slow, it means it is doing some transformation, like pitch shifting, etc. Like that. And this is the results. And you can see a text language model, never heard about music. And this is his understanding about electronic music composition. At the end of this verse, it also learns to use a sound effect. Yeah, and this is the next section. Yeah.
Sorry, does it pick the MIDI instruments as well, or is that pre-programmed for the MIDI?
So for MIDI clips, it will it will give us, say, on this track, what instrument will it be? Yeah.
Oh wow. Okay.
Yeah. So it's kind of, yeah, GPT decide that, but of course we have to use the proper timbre of that instrument.
Okay. Okay.
Yeah.
Okay.
Right. So this is more or less all about the first step I'm taken, and this is the main part of my research is to use music knowledge. And you probably know that our music knowledge is very limited. Otherwise, in this music school, we can easily teach everybody in the street about how to compose music. And this is not the case. It is just because there are some idea in our mind and it's hard to communicate. And even those words that can be communicated, they're very hard to say, to translate it into algorithms or to define it computationally. As you can see, I'm really trying a very hard approach to let the model to learn music in a very computational way. So I believe the first research question, what we can give the music is more or less like that. And another direction that interests me is think it reversely, and could AI offer us new perspective on human music knowledge? This is for AI, can it explore music knowledge on its own? And I'm only going to show you a very future directions or like with some initial results. The idea is, can machine emerge some language similar to what humans are using? For example, in this case of content and style learning, say across different domains, people understand content and style. Say on the left-hand side, it is telephone numbers. The content is the digit and style is different writing style and color. In the middle is monophonic instruments played. The content is the pitch and the style will be different instruments. And this one, for the cartoon figure or the video, the content will be different postures and the style will be different cartoon figures. People know that. And why do we know that? Our hypothesis is there is no domain-specific rules, but there is something general, which is content and style will have different pattern of variabilities. Say, for example, for the telephone number, the content digit will vary a lot on the time axis. All the number change. It is very unlikely that in the data set, all the telephone numbers are all constant numbers. It's impossible. But the style is more or less the same. It's impossible for people to write a telephone number in different style of each digit. And but if we see it vertically, we'll see that all the content, the digits, it is more or less the 10 digits, only 10. The vocabulary is small, but the style is different. Everyone writes digits in different ways. So we kind of see a dualism of different style, different variability patterns of content and style. And we try to transform that into the model losses or the model designs. And the model, without giving it much knowledge about music, or actually we didn't give any knowledge about music, the model learns what is content and style. And this is what model believes. It is, we believe a content and applied with different styles. And actually you will see that it is the same as our conception, that it is actually using the same pitch with different instruments. Yeah, and on the other hand, this is what the model believes. Say it is trying to use all the content it learns, but with a fixed style. And actually it corresponds to our, say, playing chromatic scale. Yeah. So in this process, of course, we have to give the model, say, different segmentation of the monophonic instrument clip. But other than that, there's no information about what is pitch and what is timbre. And the model tries to learn it with this kind of variability thing. So this gives to our future direction, which is through this kind of domain general rules, can model emerge a language that is actually even deeper than what is written in our textbook? Can machine understand some concepts that is as deep as the thing that we cannot express, which is in our mind? And of course, I've listed a lot of nuanced things, and there are many nuanced things I didn't list it here, like say the music has a music flow, and we have anticipation, something like that. And these are the future goal of the music AI research, is whether machine can emerge that kind of language. Yeah. So, and of course, I've shown you the potential of large language modeling, and we are trying to combine the current state-of-art model to see if we can make this generation process better. So this is about my talk, and thank you very much, and happy to see if you have questions. Thank you.
Great. Thank you to you. Any questions from people? Yeah.
Yeah, seriously, I'm flabbergasted by what you're developing, especially because there's so little that you put into it to train. I think you said 300 songs.
Yeah.
So my question is, let's say ethically or for copyright, what did you put your own compositions, or did you take? Because I know with Suno and stuff, there's like big lawsuits for what they used to.
Okay. Yeah, it's a large data set, and but for our 300 song, it is a research related. It's
Okay.
a public data set. Yeah.
Okay.
Yeah. It's like mainly from the RWC. Yeah. Yeah. Is that good?
Thanks.
Yeah.
Yeah.
Sorry, it's very kind of specific, but since you offered some really amazing higher level concepts here, but I'm really curious how you got Reaper to kind of auto-populate all of those tracks and that MIDI information. Did that come directly from a GPT prompt that you loaded into a script in Reaper, or how did you actually go about?
Okay. The idea is GPT will only give text response, but it is, say, formatted as maybe like a JSON file. And the idea is, so I think the most important part is GPT will return a list of audio clip suggestions. For the suggestion, it means it will give keywords. What's the approximate BPM, maybe the key, and what kind of chord progression is used, and we are using this keyword to search in the database, and we will get a list of possible things, and we just pick at random. It's like that. And so this is how it selects different clips, and the GPT will also give us a data structure, specify which audio clip will be placed in which section and where, and what kind of transformations it will say apply before applying on the track. Say, for example, there's a drum clip, say just a bass drum, boom. It will decide, give you a rhythm pattern. GPT will generate a list of numbers showing that if it is on the 2 and 4 or on the 1 and 3, etc. Yeah.
But you're programming it all in. You're getting the audio files. I had the impression that it was generated through maybe that was your question.
Yeah.
I had the impression that it was like some sort of script was doing it all automatically, but you created the
yeah. So the GPT only provides the data structure, and that data structure we have to write a code to convert that data structure into it. Yes.
Automatic writing of this thing. Was it done by a machine, or was the translation by a human reading stuff?
Oh, this is done by a machine, but it's by.
I think, like you show, because it was just entirely written like.
Yeah. It's by machine. So this is.
File, not MIDI file.
Sorry.
An audio file directly, right?
Yeah, the audio file is from the library. So it is just drag this audio file on it. Yeah, and with some transformations. Yeah, so actually, well, this is not my expertise, and this is actually the student I'm advising. He is very interested in electronic music, and he know how to program Reaper. So Reaper, there's an API, and with that you can say using code to do this music editing process. So through that, it can say write a code to automatically translate what GPT generates into this animation. Yeah, but it is not an accelerated version of manual editing. It is done by machine. Yeah.
In between, there is your script anyway, in between the GPT and because what GPT is it that substitute you train yourself? These GPTs that help make all these decisions.
Yes, GPT make all the decisions. We are
something you train yourself, the GPT you train yourself.
We didn't train, and what we use is in-context learning. Just like we are trying to have a chat with GPT. I tell GPT, okay, you're a music expert, and you are going to write electronic music, and we have defined a data structure for you. The data structure is you have to select clip, and the keywords must be from a list of these keywords. And and then you're going to put the clip on the music track. The way you're giving me this is you have to specify which track, which section, and yeah, like using which clip you have just mentioned, and do what operations. Yeah.
I have a question about the Hongshan, the SPLR. I think it's quite interesting as a result. I'm wondering how the model learned the intro, base, A, B, like different sections.
Okay, so at the top level of this language, there is say there is a label of the data set, say where's intro, where's verse, like that. And in the training progress, the model will just learn, say, whenever I see the top level language is intro, there's nothing on the vocal part. So it learns, say, when in the intro, there should not be any vocal melody, like that.
Thank you for the presentation. It's very, very impressive. Have you tried any other LLMs like Llama or something like this, or have you worked only with GPT?
I don't think we will try many. This is say we're still working on this project. I believe the student also tried one more, but I don't remember what's that. But mainly it's on GPT. And yeah, it's like sometimes GPT will give you some syntax error, and we have to fix that. And yeah.
Thanks a lot for the presentation. I just how does the choice of timbre at the end, like for the choice of instruments, that's an imposition of you at the end, for example, okay, I want to have the saxophone solo, and then I just use the MIDI piano rolls.
You're saying this one or electronic or this one?
For like also, how do you define the output from the timbre perspective? Because of course,
okay,
chords, pitch, and rhythm, they are okay, but then there are many other layers of music expression and performance.
Yeah, those are determined manually. So if the model generates a score, and we are trying to play it in a way that it sounds, at least we think it's better. Yeah.
And do you think this can be automatized in the future, in future research?
Yeah, I think this research I'm showing you is kind of where we want to go. Say we have some symbolic music, and we use an audio model to run it into just something from this to something. Yeah.
Am I correct in understanding that the one later on with the clarinet, like it picked clarinet, right? So that was
in this one
related. The purple spectrogram where you had the features after talking about the handwriting and the characters. There's the one where it went through all the pitches and the same timbre, and then the one where it went through all the timbres with the same pitch. You had a diagram.
You're not asking about this one?
No.
Okay.
Yeah,
this one.
this one. Yeah. So like you said it picked the clarinet. That's what it picked, right? You didn't specify clarinet.
Yeah.
Okay. Okay. So is that kind of similar then? Like it picked a timbre there, but I guess it's a lot more complicated when you're trying to combine instrumentation.
Oh, you mean if it is not monophonic sound, it is
yeah, I guess just building on what Alberto was asking about.
Yeah, it will be say if we are given model or say orchestra music, and it will be very hard for the model to extract what is timbre and what is pitch. Yeah, this is future research, but yeah, we believe to do it in similar methodologies. Yeah.
How are these sounds generated? that's which model is generating sound? Is like they're using like a computational acoustic model, or it's
You mean for this one?
yeah, for different types.
Or okay. For this one, the model just generates the audio
The
file.
model that
Yeah.
generates that.
Yeah.
Other questions? I had one, which was slide 29. I was wondering if the model could create its own forms, or if it needed to be fed them, because you said that you gave the form like this.
Yeah, it can. It can. Yeah.
So could you like input another piece, and could it learn the form of that work similar to what you do with disentanglement, where you learn the concepts, like can form be a concept that's disentangled?
Oh, you are saying the same piece but rendered with a different form.
Yeah, so like when you talked about disentanglement, you talked about taking, the chord progression
Yeah.
from one song, melodic contour of another.
I should say this is okay. For now, we cannot do this. The model just generates a form, and based on the form, it generates everything below. Yeah, it cannot do so. But yeah, so this is exactly the idea about the electronic music thing. It's actually when we compose a song, like what music material are we using, and what the form is kind of an independent thing, and we have to decide each one and then combine together into the actual song. And yeah, for now it's not supported, but definitely it's the future way.
And then also in slide 14, you were talking about polyphonic disentanglement. I was just wondering if the originals there were composed by humans, or if these were also
Yeah, originals are composed by humans. Yeah.
Okay. Thank you. All right, any other questions? Okay, thank you very much, Ziyu.
Thank you.
Just a reminder, please take some food. We have so many leftovers. Please go. And if you're interested in future meetings, please follow us on Instagram at McGill Music Research, or talk to me on ID. We also have a mailing list. Our next meeting will be December 9th at 3 p.m.